Yes, I want to record the meeting. And we have light. Yeah. Okay, here we are. I'm a little late, a little rushed, but here we are. And that is very small, so no one can see anything. Let's zoom in a little bit. Okay, so the first thing I want to start with is we have a new assignment. It's similar to the old assignment. That is, you're going to write 1 to 2 pages in this case. And you are going to, is this actually working? Sort of kind of working. You're going to write 1 to 2 pages, and then your peers are going to review it. The difference is this time we're using an old exam question. This is part of the get ready to take an exam far in the distant future, but it's going to be a written exam, not a multiple choice exam, and so it's a little different, and so I thought a little preparation might be helpful. In terms of doing this, and I think this is true of exams in general, written exams in general, you need, whenever you're writing something, you need to have an audience in mind. It's very helpful to say, because you could say, well, what background information do I have to put in? Do I have to put in 1 + 1 = 2 and show that? Right, Terence Tao takes 50 pages to prove 1 + 1 is equal to 2. So how much background information do you really need to put in there? How much can you take as given? It really depends on sort of who you're writing to. Could you grab the door in the back? Thanks a lot. And so here, we're thinking of this as an exam question. And so what you want to be showing is what you learned in class, right? You're trying to show that you learned the stuff that was presented in class. And so to do that, you need to think of what differentiates you, a person who has taken this class, from some schmuck who never had the glory of this class and had never seen this stuff, but is otherwise a perfectly good, economics student. So you think of a 3rd, 4th year student who's a good student, and they're reading your essay. And if your essay can convince them so that they understand it, that's a good essay, right? So you're trying to show that you know the stuff, and the way you do that is by teaching somebody who doesn't know the stuff. Okay? And a nice thing about this, well, first of all, that's your target audience, and that's how people are going to evaluate your thing. The people are going to give you a grade, but it doesn't count for your grade, right? Your grade is just, did you do it, didn't you do it? But in terms of what would a reader think that this thing would get, just so you have some feedback along those lines. But when it comes to your real grade, it's going to be a similar thing. I'm going to be wondering, did you understand that thing, right? And if you're skipping steps, I don't know whether you're skipping steps because it's so obvious, why need to do it, or are you skipping steps because you just don't understand those steps, and so let's skip them, right? You need to convince the reader that you understand, and the easiest way to do that is to make them understand too. So as I'm reading your exams, I'm gonna pretend like I don't know any of this stuff, and can I learn it from your essay? Which means in particular, like when you draw graphs, you need to label them well, so that somebody who doesn't know how they're labeled can figure out what's going on in the graph, right? Obviously, I've seen the graphs before, so it'll be obvious to me. But the question is, would it be obvious to someone who hasn't seen the graph before? Could someone use that graph to help them understand the material, or is it just something talking to people who already know, right? So be careful to label your graphs and that sort of thing. But also keep that in mind that that's what you're trying to do. You're trying to convince somebody who wants to learn, like they're not like arguing with you, but take someone who hasn't taken this class, a friend of yours, and take them to the point where they understand what's going on in class, right? What's going on with the material. Okay? The first round of that is going to be due on Tuesday, this coming Tuesday. This is because I know some of you have exams this week, and I don't want to get in the way of the exam, so I give you a little time after Friday to do the thing. And also next week is reading week. I cannot talk. Good grief. Next week is reading week, and so there's no classes, so the whole thing will be done by the end of reading week. So on Tuesday, end of Tuesday, you'll have it turned in, and then you'll review other people's in the rest of the week. Okay. Questions about that? Okay. Yeah.
Do you also have the reflect section from the previous assignment?
Yeah, we don't do the reflect. I would love to be able to turn that off, but the system won't let me.
All right.
If you reflect, that's fine. I mean, I assume that everybody reflects. Like anybody who wants to learn from the thing is going to reflect, and forcing them to write about the reflection, I always found dumb as a student, and so I don't make people do it. But if you want to do it, like by all means reflect. But, you know, if people say, you know, your essay was ununderstandable and strange, well, maybe they're just idiots. Like, it happens. But you're going to think, well, is that me? Is that them? Right? You're going to do that reflection. And so I don't need to ask you about that. That's my view. Like, if people have done it, you could let me know whether it was helpful or not. Like, if it was helpful, I'd assign it to people in the future. Not you, so your classmates don't kill you, but in the future. But I don't think it's valuable, so I don't make you do it. Okay, that's the assignment. Now, we're going over this McKelvey paper. Fun times. Unfortunately, I did not manage to get my pen in my rush, so I can't draw on the screen. So we're gonna make do with pencil and paper again. Sad for the people at home, but what can you do? And again, the purpose of going over this is one, we want to just get a feeling for how you could show things with any number of dimensions, right? We keep drawing things. We have a one-dimensional thing. We have a graph, so we have a two-dimensional thing, two-dimensional piece of paper, so we have two-dimensional things. But in fact, we can do this mathematically for any number of dimensions, and I want to sort of give you the vibe of how that happens. And two, I want you to sort of see what a paper looks like, because I know some of you are thinking about going on for a master's in economics, and this is kind of what it is. It will be different stuff, but this level of detail, this little slogging through the math, this is a thing, and this is what masters look like. Now, a lot of it's econometrics as well, but again, the econometrics becomes more mathematical as well. You prove the things that you're using rather than just throwing it into the computer and getting output out. And so it's going to be a lot of this similar sort of matrix algebra and stuff. So if this seems like fun, maybe a master's in economics is for you. If it seems horrific, maybe a master's in political science is for you, right? It's good to know before you get in. The thing is to match the thing you do with your skills, right? And the things that you like doing. And so you don't know what graduate school in economics looks like yet. And I'm here to tell you it looks way more like this than your current classes, okay? Just so that you have a baseline to sort of think about these things. And if you want to talk about graduate school, happy to talk to you about graduate school and what your options are and what it's like and what the vibe of the whole thing is. But that's kind of my purpose here, okay? We're going to, next time, definitely won't have time this time because it's a whole lecture. We'll go over the intuition for this paper, which is more normal, like a normal class. But here I want to give you this feeling of what's going on in these papers. So last time I think we defined a hyperplane, right? We were all busy defining. We were in the process of defining a hyperplane, this 2.6. And so 2.6, what is that saying? It's a bunch of notation. So we got H, Y, C, and that's saying we're going to take this Y and we're going to take this C as parameters. They're going to be given from the sky. We don't know where they come from. They're not something we're trying to understand. This Y and C, take any Y, any C, and importantly, Y is a vector and C is just a scalar, a normal everyday number, okay? And then we're going to take, this bracket says this is set notation. It says we're going to take all the x's, x is a vector as well, where x transpose times y is equal to c. We're going to take all of those, and that's going to define a hyperplane. So the first thing we want to talk about is what is such a hyperplane. And before I switch this off, let me go over to the camera, because I can't write on the screen, and find a pen, because that would be fun. Okay, so we've got h of yc is equal to all the x's such that x transpose times y is equal to c. Okay, that's our definition of a hyperplane. And can you read that? Yes, you can. Lovely. Okay, maybe we'll zoom in just a little bit. Now, what we want to get out of this is two things when we talk about this hyperplane. We want to have a mathematical understanding of what a hyperplane is, right? I had the example where we said, well, we had the 2D one where we said we draw a line through 2 dimensions, and I said, what if we had a 3-dimensional classroom? We'd draw a plane through it, and that would divide the class into 2. Half the people above the plane, half the people below the plane. We would do that. And then when we get to 3 dimensions, 4 dimensions, I don't know, because I can't imagine it. It's beyond my imagining. John von Neumann, very, very famously, was able to think and imagine in 5 dimensions. Good for him, that's not me. And I don't think it's anybody else, like he was like a super genius sort of guy. So it's not us. Okay, now that we're here, John von Neumann's story. So he had a boss at Bell Labs, really, really smart guy. And John was working there and he was doing his math thing, inventing utility functions and all that stuff that he did. And they went in and they had dinner at the guy's house, at the boss's house. And von Neumann sits down with the guy's 5-year-old kid, and they're just there on the floor playing with blocks and stuff. And he says, you know, John's treating him just like he was an equal. And then it dawned on him, that's what he does with me too. He was just so much smarter than anyone. Anyway, how did I get on von Neumann? Oh yeah, he can imagine things in 5, 6 dimensions. We cannot, right? We cannot. Like 3 dimensions and we're gone. We close our eyes and we get the plane going through. And so we need some kind of, what is a hyperplane in more dimensions anyway? And this is the definition. Okay? And so for this, we have our x's and our y's. Our x is just, say, x1, x2, a vector of all your policy. That is charming. Fun. Life is, I've hit freeze, that's why. Okay. That's lovely. All right. That's just your ideal policy 1, your ideal policy 2, right? Or it is, in this case, a particular policy 1 or a particular policy 2. So 0.25, 0.8, giving us the policy. We're picking a dot on this graph, and we're saying that is the policy. Right? And y, this is x, and y is equal to a1, a2, any 2 arbitrary numbers between 0 and 1, and c is just a scalar, just a number. That's any old number like 7 or 14 or 72. Okay? Any number. So we're taking all the x's where x prime times y is equal to c. Okay? So there's some notation here very clearly, right? And some of you have had matrix algebra, in which case this is clear, and some of you haven't had matrix algebra. The important thing here is I'm going to show you what happens here, but the important thing to take away from this if you haven't had matrix algebra is look, there's a whole infrastructure out there to deal with multidimensional mathematics, right? Where you're not just multiplying a number by a number, but you're multiplying a whole set of numbers by a whole set of numbers. And if I don't know what they've had in econometrics so far, but if you go on to graduate school, econometrics is chock full of this matrix algebra. It is everywhere, right? Because they want to show that, for example, ordinary least squares works if you have 2 variables that you're regressing against y, or 5 variables, or 53 variables. So they need to be able to have a math that works no matter how many variables you have. And so they use this matrix algebra. And the same thing with the data. They need the regressions to work if you have 10 observations, or 500 observations, or 50,002 observations. Right? They need to do it for any arbitrary number of observations. So they need a mathematics that works for any arbitrary number of these things. The same way, whereas we have an arbitrary number of, we can't do that here, an arbitrary number of policy dimensions, and we need it to work for any particular policy dimensions we decide to choose. In this case, 2, but it could be 53 policy dimensions. Do I have a thing? Oh, I'm so happy. I know, it's all the same to you, but it's a big deal to me. Okay. We're back over here. Okay, so that's what we're working on there. So we can go over to here and do the same similar sort of thing. And we can do slideshow from beginning. And this way, first of all, you don't have to see my hand, which is not something I'm real thrilled about. And secondly, we can show it to the people at home. Okay, so we've got h of yc is equal to all the x's such that x transpose times y is equal to c. Like so, right? And we've got x is equal to x1, x2, y is equal to a1, a2, and c is just any old number. Okay. Y and c are given to us, and x is what we're trying to find. We're trying to find all the possible x combinations such that this thing is true. So what the heck is this thing? Well, we're going to be multiplying this x with a little prime on there by y. So the first thing we're going to say is this thing here, this x transpose. What does that mean? That means x transpose is we just sort of flip it on its side. And so that's going to be x1, x2, putting the list on its side. Okay? That's what x transpose means. Okay? And then we have this mathematical thing, which is x transpose times y is going to be equal to x1, x2 times a1, a2. Okay? Says nothing to you, it's just notation. If you've had matrix algebra, it says something to you. It's not particularly difficult, it's just new notation if you haven't had it before. Okay? And when you do this, you can't see it. Oh no, you can't see it. Okay. So confused, so confused. It's going to be one of those days. Okay. So how we're going to do this, and this is just the convention, it's just notation. A multiplication, we're going to take this a times this x, the first a times the first x, plus the second a times the second x. So this thing is going to be equal to a1 x1 plus a2 x2. Okay. Just a notation they've developed so that they can do math with these lists of multiple numbers. Right? But now we can see that we have just a number, like 7 or 14 or -3. Right? It's something times a number plus something times a number. That all comes out to a number. Right? And so we can actually compare that with c, because we want all the x prime times y that are equal to c. C is just a number. These things were big matrices with lists of numbers and vectors and whatnot. But now, by multiplying them, we got them down to just a number. So we can compare these two things. Okay. So let me do it several times with various levels of dimension. So the first one, I'm going to do one dimension. Right? And we know the one dimension. We worked on the one-dimensional problem. This was the line. This is the standard Downs model. There's only one policy dimension. You could be left, you can be right, you can be somewhere in between. And so then x is just equal to x1. There's only one policy dimension. Y is just equal to a1. There's only one coefficient. And c is just, as always, just a number. And so we're looking for all the x transpose y that are equal to c. Right? That's our hyperplane is going to be any x that satisfies that equation. Okay, so x transpose y. If we flip this on its side, x transpose becomes just x flipped on its side is just the same thing because there's only one dimension to it. And that's going to be times a1, and that equals c, and so we get a1 x1 equals c. And that's our hyperplane. Or we can solve this out if we want, and we get x1 is equal to c over a1. And so on our little policy line, this is just going to be a point. Right? We started out with a one-dimensional policy space, but our solution is just a point. So it's one dimension less. Well, a point is a zero-dimensional object. We started out with a one-dimensional object, the line, and we've reduced it to a point, a zero-dimensional object, one less dimension. Right? And this is just saying a hyperplane, in this instance, is just a number c over a1. So if you give me c and you give me a1, which is what we said in our hyperplane, those were arbitrary. You give me c and you give me a1, that tells me which hyperplane this is. And that's, if I can draw it, it sort of splits this into two. We got some guys on the left, we got some guys on the right. Okay? And then, we haven't done this yet in McKelvey's paper, but then we move that back and forth until we got half the people on the left and half the people on the right to make our median hyperplane, which is what's going to give us the median voter. Right? So we did that. We changed C, we changed A1 until we got whatever we wanted. Okay? Let's do it with 2 dimensions. Right. X is equal to x1, x2. Y is equal to a1, a2, and c is, again, just a number. And so we get x transpose y is equal to c. We're going to look for all the x's where that is true. And so we get, put the x on its side, x1, x2, just the list on its side, times a1, a2 is equal to c. Multiply this out, we get a1, x1 plus a2, x2 is equal to c. And that's our hyperplane. And this, you'll notice, is just the formula for a line. So if we graph this thing, right here we got policy 1. Here we've got policy 2. And we imagine that policy 1 is 0. x1 equals 0. Then a2, x2 is equal to c, and x2 is equal to c over a2. So it's something like that. Let me do it in red. C over a2. Right? And if we continue in that vein and say, if x2 is equal to 0, then a1, x1 is equal to c, and x1 is equal to c over a1. And so if policy 2 is 0, this is, say, c over a1. And of course, we can increase. We don't just have to have them equal to 0. It can be anywhere in between as well. And so we're going to get a straight line between these two things. Right? It's not, that doesn't look super straight, but imagine a straight line. You know, I'm not going to manage it. I can erase it and do it over. It will never be straight. But this is a straight line going between this point, and that's our hyperplane. We have a 2-dimensional policy space, and we get a line going through it. A line is a one-dimensional object, one less dimension, and it's linear in a nice, linear, happy way. Right? And it has a slope. Slope equals rise over run. So if we move from here to here, the rise is negative c over a2 divided by the run. We go from here to here, so we've gone c over a1. And the c's cancel, and this becomes a1 over a2, is the slope of the line. Right. Do you see the canceling? People going, maybe? Happy with canceling? Not happy with canceling. Not if you're not happy with canceling. Okay, we're calling it people happy. All right. And so here, the important thing here is that you can really see, okay, we can calculate the slope of this line, and we can calculate the intercept. The intercept is c over a2. And so if we change c, we're changing the intercept. And if we're changing y, we're changing the slope. Right? And so when we get given these two arbitrary numbers, right, we're given, well, this is a vector. If we're given y and we're given c, we're given this line. And the c moves it up and down. And given that we have y, we're having a particular slope of this thing. If we got a different set of numbers in y, we would have a different slope of this thing. Right? Okay. Lastly, we'll do the 3 version, 3 dimensions. X equals x1, x2, x3. Y is equal to a1, a2, a3. And c is just a number. Right? And so x prime times y equals c is x1, x2, x3 times a1, a2, a3 equals c. This is a1, x1 plus a2, x2 plus a3, x3 equals c. And this is the equation for a plane. It's a linear object. Everything is linear. There's no curves involved. But we're taking a plane, and these a1, a2, a3s are going to give the angle to the plane. Maybe it's sort of slanted down through here. Maybe it's slanted back and front. Maybe it's flat. Maybe it's slanted up. That's all given by a, the a1, a2, a3. And then the c moves it up and down, or back and forth. Okay? So it's exactly the same thing, except it's got 3 dimensions. We have a 3-dimensional object, so we get a 2-dimensional plane. Okay. And clearly, if we had 5 dimensions, it would be a1, x1 plus a2, x2 plus a3, x3 plus a4, x4 plus a5, x5. Right? We can do this as many as we want. It doesn't really matter. It's all nice and linear like this. And we get an object which is linear in some sense, but 1 dimension less than what we got. And we're going to use that to split our policy space. Okay. All right. So that's sort of the infrastructure that we're using. And there's a whole bunch of infrastructure in terms of matrix algebra. So far, we've just been using vectors. But in fact, you can have multiple columns in our vectors as well. That makes it a matrix. There's a whole lot of stuff. Like, it's a huge mathematical literature. All kinds of stuff that you can do with matrices to deal with large numbers and numbers. For this paper, we only need the vectors, and so we're good with vectors. But be aware, if you go on to graduate school, you're going to deal with all that stuff. You're going to be dealing with trying to divide by matrices and stuff like that. Okay? It's all stuff that you can sit down and learn, but you will have to sit down and learn it, and you'll have to sit down and learn it pretty quickly. That's the vibe of graduate school. Okay? Now, it's lovely stuff. Like, it's really gorgeous. It's super powerful, used loads of places, but it's a thing to learn, right? It's a mathematical thing to learn. And if you're scared of learning it, it's not for you, because it would happen, right? If you went into graduate school, it would come fast, and you would have to deal with that, okay? Some of us like it, some people don't. It's up to you. Okay. Okay, so we go back over here to McKelvey. So there, in 2.6, he defines what a hyperplane is. He says we're going to take y, which is going to be the slope of our hyperplane, and c, which is going to be the height of our hyperplane. We're going to take those as given, and we've got a hyperplane. This is a very standard mathematical definition. It's nothing controversial here. It's just definition of a hyperplane. Okay. Then he starts doing stuff with it. And he's got these two things. He's got H plus, which is this, and he's got H minus, which is that. Okay? So H plus is all the, so we defined our hyperplane so that it was equal to C. And this is going to be, we're going to define it so that it's greater than C. And this one is going to be defined so it's less than C. So this is all the points above our hyperplane, and this is all the points below our hyperplane. Right? Where this same math, A1 plus x1 plus A2 x2 comes out less than C. And we can see that if we thought about it as for example, one-dimensional, right? Okay, we can actually write on this. That would be helpful. Because we're in a different program. Gotcha. If we have x equals x1, so we'll go back to our line, just a one-dimensional policy space. Then x prime y is equal to a1 x1. And we're looking for all the points, say, in this one, where a1 x1 is greater than C, right? And so that's going to be all the points where x1 is greater than C over a1. So we get like our little point, our hyperplane, which is C over a1. And this h1 plus is going to be all of this stuff here. Everything where x1, where this multiplication comes out greater than C. Right? So it's going to be not a plane, it's going to be a whole range of values. All the stuff that's to the right of this cutoff, cut off by the hyperplane. And then this one is all the stuff that's to the left of that. And if we had a plane, but if we had a line, it would be all the stuff above it and all the stuff below it. If we had a plane, it would all be all the stuff above it, all the stuff below it. So it's going to count lots of stuff, not just the line, everything above, everything below. Okay. I point this out not because it's new, but because I think it's fair to say that even when you got this, you could stare at this for a while and not know what the heck was going on, right? Like it's a little cryptic. It's simple in the end, but it's cryptic, and this level of cryptic is something that you should expect if you decide to go forward, right? It's going through these papers is not fast. It's slow reading, and you'll have to go through a lot of them. Right? Or you'll get to go through a lot of it. It's point of view of it. But it's always slow. Like it gets faster as you do more of them, but it is always slow. It's never like, oh, let me just have some light reading. No, you have to go through. You have to figure out what the heck is going on in 2.7. And you have to reason it out. You have to get out your piece of paper and pencil, and you have to figure it out. Okay. And we scroll down here, and we get our first definition that's super important to us. That's actually something. We get the definition of a median hyperplane. And that's going to be a hyperplane such that the number of people in it, so this vertical lines on either side is saying the cardinality of this thing. So we got a bunch of people in this hyperplane or in this set, all this stuff above the line, right? We've got a number of people there, so we're going to add them all up. How many of them are there? And it's going to be where there's less than or equal to half the people. There's n people. We're going to divide that by 2. So we have less than or equal to half the people above the line, and at the same time, we're going to have less than or equal to half the people below the line. And that's going to be a median hyperplane. It's going to be splitting them so that there's less than or equal to half above, less than equal to half below. Okay. Fine. Right? It's very similar to the definition we had before. It is not the same as what I told you in class. Okay? And this not the same is actually not like important to us, but it's important when you're reading papers. It's important when you're understanding papers. It's important when you're writing papers. Here, what I said was we're going to move it till there's half the people above and half the people below. Right? In which case I would say we would move this, we would pick the y and the c such that the number of people above it was equal to n over 2. half the people above. And move it so there was half the people below. Sometimes I'm a little more sophisticated and I realize there might be people on the line, and then I would say, okay, let's move it till there's the same number above as there are below, right? And so then we would say that this number would be just equal to that number. So there's the same number above as there is below, and that would be a median hyperplane. There are 3 different ways to define the same sort of thing, and in class I'm very loose and relaxed and I don't care, and so I say it in a loose, relaxed, easy to understand, as easy as I can make it to understand way. But here they have to be really precise about what they mean. And here they're defining it this way rather than my way, which is less natural and less obvious, but deals with a very specific problem. So the problem they're dealing with is one that we haven't really thought about, but is actually a thing, or could be a thing. So let me go over here and we will what is the problem? And we can see our problem if we go back to our original one policy dimension. It's a problem that we could have had from the very beginning. We just never noticed it or cared. Okay. Suppose we had one guy here, 2 guys here, 1, 2, 3, 4, 5 guys there. Okay, all at the same spot, right? And we are looking to find a median voter, right? Well, what does that median voter look like? Well, same number of people to the left, same number of people to the right. If we put the median voter, I mean, clearly it's here, right? Like, obviously it's here. If we put it farther to the right, then we've got 6 people on the left and 2 people on the right. That can't be it, right? If we put it here, we've got 7 people to the right, 1 guy to the left. That can't be it. So clearly this is the median voter. If we say, what is the guy in the middle? It would be 1, 2, 3, 4, 5. Now let me put on one more guy here. Let me put in a 3rd guy here just to make it have an odd number of voters so we're not mixed up with the odd even things. This isn't about odd and even, right? So we've got an odd number of voters, but it's still there, right? So if we sort of counted them up, we could think, well, we got 1, 2, 3, 4, 5, 6, 7, 8, 9 voters, and so it would be the 5th guy with 4 guys to one side, right? And so let me do 1, 2, 3, 4, 5. It would kind of, in some sense, be that guy, right? That feels right, and that would deal with all the proofs that we've had so far and all of that. But it isn't half the guys to the left and half the guys to the right. Here we got 3 guys on the right and 1 guy on the left. And yet this guy, I hope, feels like, yeah, he's the median voter nonetheless. It can't be anyone else. And yet it's not consistent with anything I said in class, right? Because I said half the guys on one side, half the guys on the other side. And so what do they say? Well, they say we have less than half, less than or equal to n over 2 on the right. Right? And so n in this case is 9, and so n over 2 is 4.5. So we need less than or equal to 4.5 on the right, less than or equal to 4.5 on the left. And that satisfies this. Right? So this would be our median hyperplane, in this case just a point, and it would be, yeah, right there. Okay. Okay, this is him. So here is his in English, not in math, but in English, if there is no strong total median, so no unique point where the only way that you can draw these median hyperplanes go through that point, right? Then any point in the policy space can be reached by a series of votes. So if we go back to our original sort of argument, we said, here's our policy space, and let's put a few guys in here. We know that this doesn't even have a total median at all. This was, this sort of area in here was similar to that indeterminate zone that we had in one policy dimension. And that was no big deal, because if we had lots of voters, that was going to get really small, right? And McKelvey's paper is saying, it's not quite that nice, because even if it's really small, I can take a series of votes, starting, say, from here, and through a series of votes, I can get these 3 people to vote for this. Or I can get them to vote for this. I can get them to vote for anything on this policy space. So if we don't have a strong total median, anything is possible. So the fact that this little indeterminate zone is small buys you nothing. Okay? It is true in the one-dimensional case that we talked about before. Yeah, you're going to stay more or less in that indeterminate zone. But with 2 dimensions, you can trade one policy off against the other, and you can get literally anything happening. And the trouble is there's no reason whatsoever to think we have a strong total median. Like, I can come up with examples, and I can like make it just so, and I'll do a couple next time, but I can make it just so that you do have a strong total median. But then if you move any of those guys even a little bit, that disappears. Which means if any of them ever picks up a magazine or watches a TV show or any news comes in, any strong total median is going to go away. Which means in real life, we're always going to have this problem where we can start anywhere, someplace sensible like that, and we can end up with voting for things way the heck out here, which are actually worse for everybody. Not just worse for some people. We can end up voting for things that are worse for all of us by complete democratic action. Okay. Now, we need to do the intuition for this, right? Obviously, this is, okay, there's a goofy mathematical result, what the heck? So we need to understand why it's coming about, and that will be after next week. So have a good reading week, and I will see you after. Okay? Once again, don't forget the assignment.